Hi, I'm Carissa Slone. I'm getting my PhD at the University of Kentucky under the guidance of Bert Yu. And today I'm going to talk about Klein Four slices of Eilenberg-Mac Lane spectra. My primary focus is on the slice filtration. It was developed by Hill, Hopkins, and Ravenel in their solution to the Curvaire invariant 1 problem. What the slice filtration does is that it decomposes genuine G-spectra into building blocks, which we call slices. Today, we're using the regular slice filtration from Ullman, whereas Hill, Hopkins, and Ravenel use the classical slice filtration. The results are the same, except for an indexing difference of 1. Let's define the slice filtration. Tau at least NG is the localizing subcategory of genuine G spectra generated by jet spectra of a particular form. We have a localization functor, P lower star from genuine G spectra to tau at least star G, natural maps from P lower n to P lower n minus 1, and then fiber sequences from P lower n plus 1 of x to x to P upper n of x, where x is some genuine G spectrum. The goal with the slice filtration is to determine the slices of x and the corresponding slice spectral sequence. Those fiber sequences I mentioned also fit together into what's called the tower, and if possible, we want to determine the tower of x as well. Another interesting thing with the slice filtration is characterizing slices over some group G. Due to results from Hill, Hopkins, and Ravenel and Ullman, we only need to characterize n slices, where n is between 0 and the order of g minus 1, to have a complete characterization of slices over G. Hill, Hopkins, and Ravenel characterized the 0 and 1 slices, and Ullman characterized the -1 slices, and this is all over some finite group G. For Klein Four, then, we're only missing the 4k plus 2 slices. So let's remind ourselves what a Klein Four Mackey functor looks like. L, D, and R are the right, left, diagonal, and right subgroups of Klein Four respectively. Then the Lewis diagram takes this form. We have an MK4 at the top, an ML, MD, an MR in the middle, and an ME at the bottom. And then we have our restrictions, which are the maps going down, and our transfers, which are the maps going up. We also have a vial group action at each level, and if we don't indicate the vial group actions for a specific Mackey functor, then they're trivial. For example, we have the constant Mackey functor Z. It has a Z in each spot. The restrictions, the blue maps going down, are the identity, and the transfers, the orange maps going up, are multiplication by 2. And because it's a constant Mackey functor, all of the vial group actions are trivial. Next up is this Mackey functor G, which is a single copy of F2 at the top and zeros everywhere else. The restrictions and transfers are all trivial, in which case I'm not going to draw them. And then finally, if we move the F2 to the bottom and put zeros everywhere else, that Mackey functor is called F. Now we're ready to characterize 2 slices over Klein Four. Suppose the only non-trivial homotopy of a K4 spectrum X is pi1 of X and pi2 of X, where we have a few conditions. The restrictions of M need to be injective, and the sequence mapping from MK4 to ML plus MD plus MR via the sum of the upper restrictions, and then mapping to 3 copies of ME via the sum of this matrix involving the lower restrictions. This sequence needs to be exact. Our second condition is that the group at the bottom of our pi1 is 0. And then our third condition is that when we map from NK4 to NL plus ND plus NR via the sum of the upper restrictions, that map needs to be injective. If all 3 of these conditions are met, then X is a 2 slice. Conversely, if X is a 2 slice, then its only non-trivial homotopy is pi1 of X and pi2 of X. For the twofold suspension of our H pi2 is a 2 slice. And the one-fold suspension of our H pi 1 is in the interval from 2 to 4, i.e. conditions 1 and 2 hold. It's not necessary for condition 3 to hold for x to be a 2 slice. For example, we'll take x to be this ROK4 graded suspension of HE, where E is this Mac functor. Then x is a 2 slice with pi 2 equal to f and pi 1 equal to g. But the one-fold suspension of HG is not a 2 slice, it's actually a 4 slice. Now, a lot of work has been done computing slices of particular Eilenberg-Mac Lane spectra. For example, Hill, Hopkins, and Ravenel in 2017 computed the slices of sigma infinity lambda HC p to the nz, where p is an odd prime. Ravenel in 2017 computed the slices of sigma n HC p to the nz and sigma n HC4z. Zhao in 2018 computed the slices of sigma n D2nz. And then Yu Yarnall in 2020 computed the slices of sigma n HK4F2, where F2 is the constant Mac functor. Aside from Ullman, not much work has been done regarding D-suspensions of Eilenberg-Mac Lane spectra. In my paper, I compute the slices of sigma plus or minus n HK4z. For n between 0 and 5, it turns out that sigma n HZ is an n slice. Then for every other value of n, the slices of sigma n HZ are ROK4 graded suspensions of Eilenberg-Mac Lane spectra. Let's take a look at an example. Here we have the cotower on the left for sigma minus 1 HC. It has a -4 slice, a -2 slice, and a -1 slice. On the right, we have the tower for sigma 7 HC, and it has a 12 slice, an 8 slice, and a 7 slice. Now you might notice that the spectra, the slices in the right tower, are the Anderson duals of the slices in the left cotower with a shift by rho K4. This is not a coincidence. There's actually a really nice interaction between Anderson and Brown-Kamenetz duality, which results in this duality between the slices of sigma minus n HC and sigma minus n plus 8 HC. My current work has to do with Q8 equivariant homotopy theory, where Q8 is the quaternions. This work is joint with Berg-Yu. First, we're looking at the slices of sigma plus or minus n HQ8z, and then we want to replace z with F2. And finally, we really want to characterize the n slices over Q8. That's all I have for you today. Thank you for listening.